Good morning, y'all. Today we're going to be talking about solving differential equations. It's our first notes in chapter 6. We've talked about differential equations a little bit before. Differential equation is just an equation that involves dy dx, so the derivative, and then x and y, or just x. It can kind of have a combination of all of them. So we're going to look at number 1. And just like before, our first step with a differential equation is I want to multiply that dx over, so it's with all the x's. So I'll have dy on the left, and I'll have dx on the right. We call this form separate and integrate. Now, usually, with what we've dealt with so far, we've only had x's on one side and then dy over dx on the other side. Sometimes we'll have x's and y's on both sides, so that separate and integrate really means to get all of your y's by themselves on the left side and all of your x's by themselves on the right side. But let's look at number 1. So number 1 is a little bit easier because we just have to deal with moving that dx over. So before I am integrating, I multiply dx over, so we get dy, a little thick for my preference. We get dy is equal to 10x squared over the square root of 1 plus x cubed times dx. So first I separate, then I come in and I integrate. Okay, so on the left side, my integral is going to be pretty easy. The integral of 1 dy is just equal to y. Okay, on the right side, that's going to be a u substitution integral. So my u is going to be what's trapped down here in the bottom, 1 plus x cubed. So u is equal to 1 plus x cubed, which means du is equal to 3x squared dx, which means du divided by 3x squared is equal to dx. So then I can go ahead and plug that into my integral. So this becomes the integral of 10x squared over u to the 1/2 times du over 3x squared. X squared and x squared is going to cancel out. Still, before we've actually integrated this, we end up with y is equal to 10 thirds out front, so 10 thirds times the integral. Move that u to the 1/2 up to the top, so it becomes u to the negative 1/2. And then, of course, du. And now I can actually integrate. So this becomes y is equal to 10 over 3 u to the 1/2 divided by 1/2, because I add 1 divided by the new power. And then, of course, it's an indefinite integral, so I tack on my plus c. Now this becomes y is equal to 10 over 3 times 2 over 1. U is now 1 plus x cubed to the 1/2 power plus c. So as my final answer, we get y is equal to 20 thirds times the square root of 1 plus x cubed plus c. So same sort of process so far as we saw in chapter 5. Just multiply that dx over, and then I'm going to integrate it like normal, applying any integral rules or integral properties that I have to be able to take that integral. So pretty straightforward on number 1. Let's look at number 2. And number 2 is going to be really what I'd say we consider to be our chapter 6 differential equations. So we have y prime is equal to 2x over y. Okay, so first and foremost, y prime, I can go ahead and change that because y prime is the same as dy over dx. And the reason why I'm changing that is because I need to have dx over on one side and dy on the other. So I can't leave it as just y prime. And then over on the right side, I still have 2x over y. Okay, as my next step, I need to get y's over on the left side and x's over on the right side. So I can multiply y over, so that becomes y dy, and I can multiply dx over, which makes this 2x dx. And then I'm going to integrate both sides, so integral of y dy, integral of 2x dx. On the left side, instead of getting just y, now I get y squared over 2. And over on the right side, 2x becomes 2x squared over 2. And then, of course, plus c. Hey, now, I can technically, at this step, leave my answer like this. Okay, but sometimes the question is going to ask you to actually solve for y. And if you need to solve for y as your final answer, you cannot leave your equation as that big, long mess. Okay, so we do have to actually solve this out for y. So if I wanted to solve this for y, then first things first, I can multiply that 2 over. So this becomes y squared is equal to 2x squared plus c. Notice how I didn't multiply the c by 2. So we kind of treat c as this extra ambiguous little thing that we don't really multiply or divide by any of our constants that are being moved. Okay, then last and not least, I'm going to take a square root to both sides. So y is equal to the square root of 2x squared plus c. And just as an extra tidbit, because we're not actually evaluating and we are leaving this in a function, we do write it as y is equal to the positive or negative square root of 2x squared plus c. And that would be our final answer if we were solving all the way out for y. So just kind of notice the slight differences between that and the other answer that we got. So this one is also correct, but if we wanted to solve it out all the way for y, then we get positive or negative square root of 2x squared plus c. Okay, let's keep looking at some more. So number 3, we have y prime is equal to the square root of x over 3y. So same thing. First and foremost, I want to change that y prime to be dy over dx. And then, of course, over on the right, I still have square root of x and 3y. So then I can multiply the y over, multiply the dx over. So this becomes y dy is equal to 1/3 x to the 1/2. I'm just going to go ahead and change that since I know I need to integrate. Integrate and integrate. One thing I want to point out is that I didn't multiply over the 3. You can multiply the 3 over if you want to. It doesn't matter if it's over with the y or if it's over with the x. It will all work itself out in the end, wherever your constant is on either side of the equation. Because if you end up solving for y in the end, you would still then multiply or move that constant back to the other side. So since I would have to move it back if I was solving for y, I like to just keep constants on the right side if I can keep them on the right side. So instead of multiplying over by the 3y, I just multiplied over by the y. So from here, we just integrate both sides. So y becomes y squared over 2 equals 1/3 x to the 1/2 becomes 1/3 x to the 3/2 divided by 3/2. And then, of course, plus c, which becomes y squared over 2 is equal to 1/3 times 2/3 x to the 3/2 plus c, which becomes y squared over 2 is equal to 2/9 x to the 3/2 plus c. So once again, we could leave it like this if we didn't have to solve for y. If we did need to solve for y, we could keep going by moving that 2 in that square root. So this becomes y squared is equal to 4/9 x to the 3/2 plus c. And then y is equal to the positive and negative square root of 4/9 x to the 3/2 plus c. Okay, so that's our all the way solved, wrong color, for y answer. So just a little bit extra to solve all the way out for y, but you don't have to unless the problem denotes it. Okay, last of our basic, what we call our general solutions. Okay, we have x squared plus 4 times dy over dx is equal to xy. Okay, so right off the bat, I don't have to change that y prime to be dy over dx. It's already dy over dx. Okay, but I can go ahead and divide the x squared plus 4 over, multiply the dx over, and divide the y over. So this becomes dy divided by y is equal to x over x squared plus 4 dx. And I can integrate both of my sides. Okay, so over here on the left, the integral of dy over y, that's the same as 1 over y times dy, which is actually the natural log of the absolute value of y. Okay, so a little different. Now I have the natural log of y. So instead of getting y squared over 2, now I have the natural log of y. And this is actually a really common integral that we end up with differential equations. So you're going to be really used to integrating and getting this natural log of y. Okay. On the right side, we have x over x squared plus 4. That is going to be a u substitution. So u is equal to x squared plus 4, which means du is equal to 2x dx, which means dx is equal to du divided by 2x. So from there, I can go ahead and plug in. So this becomes the integral of x over u times du over 2x. We get x's and x's to cancel out. So then this becomes the natural log of the absolute value of y is equal to 1/2 times the integral of 1 over u du, which once again also becomes the natural log of u. But then of course this time, because it's my right side, I'm going to tack on that plus c. Okay, so from here I just need to plug back in my x, so we get natural log of absolute value of y is equal to 1/2 natural log of the absolute value of x squared plus 4, and then of course your plus c. Okay, so this is our final answer if we are not having to solve for y. If we have to solve for y, I only have to do one little step on the left side to get y by itself. And you might have remembered this from pre-calculus / algebra 2. You might have forgotten it. But when I have something being taken to a natural log, I can get rid of that natural log by taking everything to a base of e. So right here on my answer, I can take everything to a base of e. On the left side, the e and the natural log, those cancel out because they have the same base. So I'm left with just y. On the right side, I have e 1/2 natural log of x squared plus 4 plus c. So I can separate that into e to the 1/2 natural log of x squared plus 4 times e to the c. Because one of my exponent properties, which I conveniently attached over here, is that if I have two exponents being added, here our product of a power, two exponents being added in the same power, I can separate into two of the same base of those separate pieces that are being added. So that's how I can split this up. Now, the reason why I split this up is because, for one, I'm going to be able to actually get this first part to cancel out a little bit more. For two, e to the c is actually a super important result in differential equations. E to the c is what we refer to as big C. Okay. And Miss Reichard, when you have her in BC Calculus, she's going to get mad at you that I call it big C. But I call it big C because I think it's easiest to remember. So big C happens when you get this e to the c result. So anytime you have a natural log of y, you know your final answer is going to be big C. And this big C shows up all the time in differential equations with growth and decay and all this sort of stuff that involves e. So it's a really important result in calculus. But essentially, big C just becomes kind of like this big constant that's being multiplied in front of your function. So my new function becomes y is equal to big C. So y is equal to c times, and then I'm going to get my e's and all this kind of mess. Okay. So I have e to the 1/2 natural log of the x squared plus 4. So before I can get that e and natural log to cancel out, I actually have to move that 1/2 power to the inside. That's another one of my properties. It's a property of logarithms that if I have a constant being multiplied out front, I can move that constant in. So p times log base b of m is the same as log base b of m to the power of p. So I can move that power to the inside. So this becomes c times e to the natural log of the square root of x squared plus 4. Okay. Now, once I change it here, then I can get that e and natural log to cancel out. So this becomes y is equal to just big C square root of x squared plus 4. And that is our final answer. Probably not going to get it. Okay. So significantly different than our one that's not solved for y. And you're probably thinking right now, Mr. Arbone, what is this? This is so much extra work. The good news is this is chapter 6. This is the bulk of chapter 6. It's just doing this skill. It's just solving for y, solving for c, these sort of values. So while this is hard, this is also the only thing we're going to do for the next 2.5 or so weeks. Okay. So these are all what we call general solutions, because general solutions are where we finish it out and we just have C. A particular solution is when we plug in and actually solve for that value of C. So find the particular solution of each differential equation with the given initial condition. Okay, so on number 5, we have dy over dx is equal to 3/4 y. Okay, so same as always, separate, separate, integrate, integrate. That's our first step. So our first steps, I'm going to divide that y over. So we get dy divided by y is equal to, multiply the dx to the other side, 3/4 dx. And then I'm going to integrate both sides. Okay, even though I don't have an x on the right side, 3/4 is just a constant I can integrate to get 3/4 x. On the left side, dy over y does become natural log of y. So natural log of the absolute value of y is equal to 3/4 x plus c. Okay. Now, yes, I could go ahead and solve out for y right now, but I personally think that's a little bit difficult, and I think it's significantly easier to immediately after you integrate, solve for your value of c. So we're going to go ahead and solve for our value of c immediately. So right here, natural log of the absolute value of 10 is equal to 3/4 0 plus c. So from here, 3/4 times 0, that cancels out. So we get natural log of 10, because absolute value of 10 is just 10, is equal to c. So now I can plug that back into my function. So this becomes natural log of the absolute value of y is equal to 3/4 x plus the natural log of 10. And if I don't have to solve for y, this could be my final answer. But if I have to solve for y, I do have to do just a little bit of extra work to solve out for y. Okay. So if we are solving for y, I'm going to take that base of e to both sides. So base of e base to e, that gives me y is equal to e to the 3/4 x plus the natural log of 10. From here, I can separate that out into y is equal to e to the 3/4 x times e to the natural log of 10. Now, I'm not going to get e to the 3/4 x to cancel out, but I am going to get e and my natural log here to cancel out. And so that 10 ends up then just being a constant multiplied. So for our final answer, we get y. We get y is equal to 10 e to the 3/4 x. So notice how, for our final answer in this one, our constant, our c value essentially, became just this big constant number multiplied in front. That's why over here, we just say e to the c is equal to big C, because if we're getting that e to the c result, then we know we're going to have the same thing happen every time. Our c value is going to be the natural log of some number, and then when we finally solve out for y, we'll get e to the natural log of that number, and we'll end up getting that big number multiplied in front. So that's why we can say e to the c is just equal to big C, because we know that result's always going to hold true. Okay, so that is our all the way solved out for y answer. All right, let's look at another one. So number 6, we have dy over dx is equal to x squared over y. Y of 3 is equal to -2. So same thing, separate, then integrate, integrate. So dy becomes y dy is equal to x squared dx. Then we integrate both sides. So integrate, integrate. This becomes y squared over 2 is equal to x to the 3rd over 3. And then, of course, plus c. Now, once again, I like to plug in for my c immediately. So -2 squared over 2 is equal to 3 cubed over 3 plus c. From here, -2 squared is 4 over 2 is equal to 3 cubed is 27 over 3 plus c. So 2 is equal to 9 plus c, which means -7 is equal to c. So I can go back up here and I can plug this in. So y squared over 2 is equal to x cubed over 3 minus 7. Then, of course, I still want to solve out for y. So I can multiply 2 to both sides. So we get y squared is equal to 2x cubed over 3 minus 14. And then take a square root of both sides. And we get y is equal to the positive and negative square root of 2x cubed over 3 minus 14. So right up here, this, of course, would be our not solved for y answer. And then just below this would be our solved for y answer. Okay, so hopefully at this point, we've gone through 6 different problems. You're kind of starting to get the feel for it. Separate, so you get y's on one side, x's on the other. If you are just solving for the general solution, so that means you don't have an initial condition. That's the difference. These, we don't have initial condition. It just says solve the differential equation. These, we do have an initial condition, and it says to solve for the particular solution. So that's the difference. It gives you an initial condition, and it asks you to solve for the particular solution. Okay, you can, of course, leave them as all not solve for y, as long as it doesn't say solve for y or find y equals or find an equation for y. If it says anything about finding y or finding f of x is equal to y or something like that, then you have to solve out for y for the final answer. Okay, I'm going to let you go ahead and pause me. And I want you to try and do 7, 8, and 9, 10 on your own. And then I'll talk about them at the end real quick. But I just don't want to make the notes video too much longer. Okay. All right, y'all. Let's look at these. Just talk about them real briefly. So number 7, a little bit crazy. So if 7 is the one that threw you off, that's okay, because 7 is kind of hard. So on the left side, we have e to the 2y, which is going to be a u substitution. You can see we take that 2y out, which gives us that extra 1/2. On the right side, it's just 3x squared, so 3x cubed over 3. As we solve out, we plug in, we get 1/2 e to the u is equal to x cubed plus c. So that's my function. Plug back in for u. We get 1/2 e to the 2y is equal to x cubed plus c. Then plug in from there, plug in 0.5, plug in 0. We get e over 2 is c, which is a little bit of a weird value, but it's okay. We can get weird values. Remember, this is non-calculator, so we're going to leave it as e over 2. And then we plug back in. 1/2 e to the 2y is equal to x cubed plus e over 2. If you don't have to solve for y, you can leave it like that. If you do need to solve for y, this time, instead of taking everything to a base of e, I have to get rid of that base of e. So I multiply the 2 over, which gives me 2x cubed plus e. And then I take both sides to a natural log. So instead of taking everything to a base of e, I take the natural log of both sides, which gets the e to cancel on the left. And then my whole right side is inside that natural log. Lastly, dividing over that 2, which gives us 1/2 natural log of 2x cubed plus e. Okay, on 8, this one's easier on the y side, y, which just becomes y squared over 2. On the right side, we get that 1 plus x over x. That's that polynomial over a single x, so split it up and then simplify from there before we integrate. So when we split up into 1 over x and x over x, that becomes 1 over x plus 1. Integrate 1 over x in the natural log of x, integrate 1 into x. Plug in our values. Natural log of 1 cancels out to be 0, so we end up getting 7 for c. And then solve all the way out. That one's a little easier. Multiply the 2, square root the y. So we get positive or negative square root of 2 natural log of x plus 2x plus 14, or our unsolved one if you do not have to solve for y. Over on number 9. This one's a little bit really pretty easy altogether. Multiply the y over. Integral of y is y squared over 2. Integral of 1 plus x is x plus x squared over 2. Plug in our values. We get 2 for c. Plug that in. You can leave it unsolved for y, or you can solve it out for y. And we get positive or negative square root of x squared plus 2x plus 4. And last but not least, y'all, number 10. Number 10, we get that dy over y, which gives us a natural log of y, which when we plug in, we get the natural log of 7 is equal to c. So we can leave it as the natural log of the absolute value of y is equal to 4x squared plus natural log of 7. But if I need to solve for y, then I take that base of e to both sides, which gives us y is equal to e to the 4x squared plus natural log of 7. Splitting that up into e to the 4x squared times e to the natural log of 7. E to the natural log of 7 cancels out and gives us that big 7 multiplied in front, because that really is our e to the c form, which gives us big C that we talked about before. Okay, so that is differential equations, y'all. As you start to do them, and we're going to do a lot of them because like 99% of chapter 6 is just taking and solving and evaluating differential equations. We're going to learn 6.1, which is 2 kind of small little extra things, but really differential equations is the vast majority of chapter 6. So we've learned like all of chapter 6 already on day 1. Okay, so we're going to practice these and practice these and practice these some more. So if you don't quite understand all of these today, that's okay. You're going to get lots of opportunities to work on them. But of course, if you have any questions, we'll talk about them in class. Thank you much.